Good evening, students. Welcome to the third lecture for solution of triangles. Okay, so पहले दो lectures में मैंने आपसे कुछ basic concepts के बारे में बात करी, जैसे sin rule, cosine rule, projection rule. ठीक है, तो वो हमारे पास basic formula थे, तो वो आपने videos देखे होंगे, correct? So now I'll be like continuing with the third lecture. So in the third lecture, I'll take the concept of orthocenter. ठीक है, ऑर्थो सेंटर की अगर हम बात करें, if we talk about orthocenter of a triangle, orthocenter basically means that it is the point of intersection of altitudes of a triangle. Okay, so if I draw a triangle, say this is the triangle ABC. If I draw this triangle and I draw three altitudes, one altitude from A to BC, then one altitude from B to AC, which will be BE, and one altitude from C to AD, which will be CF. So we know that for any triangle, the three altitudes of a triangle are concurrent. So this point of concurrency is called the orthocenter of a triangle. This point of concurrency is called the orthocenter of a triangle. For any triangle, if we draw altitudes, the three altitudes, they are always concurrent, irrespective of how the triangle looks like. And the point of concurrency, which means the point of intersection of the altitudes, is called orthocenter. Okay, then we can classify into this into three categories. First is case 1. For case 1, I take the acute angle triangle. So if for an acute angle triangle, the orthocenter always lies inside the triangle. For an acute angle triangle, orthocenter always lies inside the triangle. Okay, so acute angle triangle, orthocenter lies inside the triangle. Okay, now if we take case 2, in case 2 we have obtuse angle triangle. Okay, in case 2 we have obtuse angle triangle. Now for an obtuse angle triangle, if we take the three altitudes, for an obtuse angle triangle, if we take the three altitudes, then if we draw the altitude, like if I draw the altitude from B, it will be like this. If I draw the altitude from C, it will be like this. Okay, and if I draw the altitude from A, it will be like this. Okay, so these three altitudes, if I draw the altitude from A, it will be like this. So these three altitudes will meet outside the triangle. Okay, so because this angle is like more than 90, so if you draw the diagram of an obtuse angle triangle, it will always be like that, that whenever we form the altitudes, two altitudes will be going on the outside of the triangle, and therefore the three altitudes will meet outside. Okay, so for an obtuse angled triangle, if we talk about orthocenter, that is always lies outside the triangle. Okay, for an obtuse angle triangle, orthocenter always lies outside the triangle. And now if we take case 3, for case 3 I take the case of a right angle triangle. So for a right angle triangle, I have, say this triangle is ABC. For a right angle triangle, if I say I want to draw altitude from A to BC, so altitude from A to BC will be this line only, AB, because this is perpendicular to BC. Okay, so one altitude is this, and if I say that I want to draw altitude from C to AB, so altitude from C to AB will be this line BC. Okay, and if we can say, if I draw altitude from B, so I take the altitude as BD. So these three are the altitudes of this triangle. From A to BC I have AB, from C to AB I have CB, and from B to AC I have BD. So we can see that these three altitudes meet at the point B, which means in the case of a right angle triangle, B is the orthocenter. In the case of a right angle triangle, B is the orthocenter, which means for a right angled triangle, the orthocenter lies on the triangle. For a right angle triangle, orthocenter lies on the triangle, and it is the vertex where we have the right angle. Okay, and it is the vertex where we have the right angle. Okay, so in these three cases we can say that means these cases comprise the different categories in which we can define orthocenter. Okay, now I will like continue ahead. with some more concepts. Uh, just 1 minute. So now if we continue forward, we can say for if I draw a triangle like this, okay, and I draw the circumcircle for this triangle. So the circumcircle for triangle is a circle passing through the vertices of the triangle, that we already know. Okay, this triangle is ABC. If suppose I want to find the orthocenter, so what I will do, I will draw the different altitudes. So this altitude, and then this altitude. So this point will be the orthocenter. So there is one important property of orthocenter, that if we take the image of orthocenter about any side, okay, if we take the image of orthocenter about any side, then that image always lies on the circumcircle of the triangle. Which means if suppose I take the image of H about BC. So image of H about BC lies on this circumcircle. Okay, so that we have to prove lies on circumcircle. This is the property. Okay, we can take the image of H about any side. If I take the image of H about this side AC, then this will lie on this circle, this point here on the circle. And if I take the image of this point about this side AB, so then again it will lie on this side. Okay, so I'll take just one case. Whether you take the image about any side, it will always lie on the circumcircle. Okay, so suppose this point is E, and if I extend this point is F. Okay, so now if we consider triangle BHE and triangle BEF. If we consider triangle BHE and triangle BEF, this angle, if I say this angle will be equal to this angle, because this is the property of circle. This point is connected to this chord like this, and this point is also connected to the chord. So angles drawn in the same arc are always equal. This we have already studied in classes 9 and 10. So which means this angle will be equal to this angle, correct? Now we can say that okay, if I talk about this angle, this angle will be pi by 2 minus c, because if we consider take this point as G, so in triangle BGC, if we take this triangle, in triangle BGC, this angle is 90 degree. Therefore sum of these two angles must be 90. Sum of these two angles must be 90. Now if this angle is C, therefore this angle must be pi by 2 minus C. This angle is pi by 2 minus C. So if I take this angle will be equal to C, correct? Because this is a right angle triangle, so obviously sum of these two angles has to be 90. Sum of these two angles has to be 90, and this angle is pi by 2 minus C. Therefore this angle will come out to be C. And this I already told you that this angle and this angle will be equal. Angle ACB will be equal to angle BFA. Angle BFA will be equal to angle ACB, because angles drawn in the same arc of a circle are equal. Angles drawn in the same arc of a circle are equal. So which means this is equal to angle C. So this is also angle C, and this is also equal to angle C. So now if we consider these two triangles that I have written here, triangle BHE and triangle BEF. Angle BHE will be equal to angle BFE. Angle BHE will be equal to angle BFE. Okay, and these two angles will be equal. angle BEH equal to angle BEF equal to 90 degree. Okay, and obviously if these two angles are equal, both these angles are equal, so this angle will also be equal to this angle. Both of these two angles will also be equal. This is pi by 2 minus c, so this angle will also be pi by 2 minus c. So now these two angles are equal. This is the common side, DE is common side, and these two angles are also equal, 90 each. So by ASA congruence theorem, I can say that triangle BEH will be congruent to triangle BEF. Okay, by ASA, angle side angle congruence theorem, I can say triangle BEH will be congruent to triangle BEF. So now once I have proved the congruence of these two triangles, I can say by CPCT, which means corresponding parts of congruent triangles, corresponding parts will be equal. So which means EH will be equal to EF. Corresponding parts of congruent triangles will be equal. So EH, this length will be equal to this length, EF. So if this length is equal to this length, we can say that the image of this, whenever we talk about image, we take the equal distance on the opposite side. So if I want to take image of H about BC, I will take the same distance on the opposite side of BC. So same distance, this is same distance on the opposite side, so this will come out to be F, which means F will be the image point for H, and F is already lying on the circumcircle. So this is what we wanted to prove, that if I take the image of orthocenter about any side, so the image point will always lie on the circumcircle of the triangle. Okay, so this was one property, important property, that I wanted to prove. And now continuing forward, we can one more concept related to orthocenter only is the distance of orthocenter from the vertices and the sides of the triangle. Okay, so I have the orthocenter, but what I need to find is, I need to find the distance of orthocenter, distance of H, I am saying orthocenter, from sides and vertices. Okay, distance from orthocenter from sides and vertices. Okay, so if I draw this triangle, this is the triangle ABC. Okay, and the diagram will be similar. I will draw three altitudes, this altitude, then this altitude, and then this altitude. So this is the point of concurrency, which means this point will be the orthocenter. So basically here I am interested in two things. First thing is, I want to find the distance of orthocenter from any one vertex. So suppose we are talking about A, so I want to find the distance AH. And second thing is distance of orthocenter from the side. So basically HF or HE you can say. Okay, so a formula for finding the distance of orthocenter from any one vertex I should know, and formula for finding the distance of orthocenter from any one side, that is also important. Okay, so by standard notations, this length is A, this length is B, and this length is C. Okay, so if we apply trigonometry in this triangle, in triangle AFC, if I apply trigonometry, cos of A, okay, this is a right angle triangle, so cos of A is base upon hypotenuse, which means AF upon AC, and AC is nothing but B, so it will be AF upon B. Now if you cross multiply, so AF will become B cos A, AF will become B cos A, right? Okay, so AF is B cos A, and now I want to find the length of AH. Okay, so I got the length of AF as B cos A, but now I'm interested in finding this length AH, which means I need to apply trigonometry in this triangle. So in triangle AFH, if I take this angle, cos of this angle, say cos of theta. Okay, I take this angle, cos of theta. So cos of theta is base upon hypotenuse, which means base is AF upon AH. AF we already know is B cos A. So I substitute B cos A here, and AH will come in the denominator. Okay. So cos theta is equal to AF upon AH. AH is what we are trying to find. So AH is the unknown quantity and AF is already we calculated earlier. So B cos A. So in place of AF I substituted B cos A, and now I want to find cos theta. So for cos theta, basically yes, if you see in this triangle, this angle is B and this is 90 degrees. So sum of these two angles will be 90, which means theta plus B is equal to pi by 2. If we take in radians, so this is a right angle triangle, this is already 90, this is already pi by 2, which means these two angles will be complementary. So theta plus B is 90 or pi by 2, which means theta will be pi by 2 minus B. So I can write theta as cos of pi by 2 minus B is equal to B cos A divided by AH. Now cos and sin are complementary. So cos of pi by 2 minus B can be written as sin B. So sin B is equal to B cos A divided by AH. Now AH will come here and sin B will go in the denominator. So it will become B cos A upon sin B. And already in the sine rule I told you that whenever we take the ratio of any side divided by sine of the angle, so we get 2r. So B upon sin B from sine rule can be written as 2r, 2 times the circumradius. So we get the formula for AH. AH means the distance of orthocenter from the vertex A. So AH is 2r cos A. Similarly, we don't need to prove for other vertices. Similarly, we can relate. So BH will become 2r cos B and CH will become 2r cos C. So AH is 2r cos A, BH is 2r cos B and CH is 2r cos C. Okay. So one part I did, like I wanted to find distance of orthocenter from side and vertex. So vertex I have already found out. Okay, I derived for distance from orthocenter from A, and similarly we can say for BH and CH also. Now we come to the other part, which is how to calculate the distance of orthocenter from any side. Okay, how do I calculate the distance of orthocenter from any side? So which means now I am interested in finding this distance FH. Okay, so for FH, I can, so this we already did, that AF is equal to B cos A, and so now we need to apply the trigonometry in same way. We need to apply trigonometry only. Okay, so if we take triangle AFH, in this case I need to take tan, because I am interested in finding this distance FH. I am interested in finding this distance, so that is why I need to take tan of here. So tan of theta is perpendicular upon base, so therefore perpendicular is FH upon base is AF. So FH upon AF. Now AF I already calculated earlier, so in place of AF I can write as B cos A. So B cos A will come here and FH will come in the numerator. So FH upon B cos A, and theta, I told you that this is a right angle triangle. So sum of these two angles is 90, which means theta I can write as pi by 2 minus B. So in place of theta here you can write as tan of pi by 2 minus B. So this will become cot B. So cot B is equal to FH upon B cos A, which means FH can be written as B cos A into cot B. Cot B can be written as cos B upon sin B. And similarly by sine rule we can say B upon sin B is equal to 2R, because like I already used it in the previous derivation also. So in place of B upon sin B, using sine rule we can write this as 2R. So 2R cos A cos B. 2r cos A cos B will be the formula for the distance of orthocenter from any one side. So if I want to find the distance from AB, so in the formula the terms will contain the angles A and B. So FH will be 2r cos A cos B. Similarly, if I want to find this distance EH, so EH basically E is lying between A and C. So EH will be 2r cos A cos C. And if I want to find this distance DH, so D is lying between B and C, so DH will be 2r cos B and then cos C. So similarly we can say for other two lengths. Okay, so this is how you find the distance of orthocenter from any one vertex or any one side. Okay, so in today's lecture, like we focused on what is the definition of orthocenter, and I took different cases. Like for acute angle triangle, obtuse angle triangle, and right angle triangle. And then I took two properties. Okay, so I think this would be enough for this lecture. And now basically we are left with pedal triangle and like some properties related to that, which I'll be taking in the fourth video. Okay, so for now it would be enough. Okay, so thanks for like listening to this lecture.